Bismillahirrahmanirrahim. Assalamualaikum. And okay, we'll continue with the design of the digital feedback controller uh, from the discrete time that we introduced last week. Basically, the analog representation for the PID controller is just what we have seen before, okay, in your previous class. The PID, or in terms of the time domain, or in terms of the S transformation, okay. This is the time domain S transformation. So we want to convert into the for use in the discrete time, we have to discretize it first. So for the integral, we use discretize using rectangular integral method. You've seen before, maybe in your mathematics class. For the derivative, we use the first order difference method. So when we discretize them, for this one, we'll get the En plus discretize into the rectangular integral. So we get this sampling time over tau 1, okay, summation e to k. We discretize using first order difference, we just get t over t En minus En minus 1, ever at n minus En minus 1 plus the constant value or the nominal value. And this is called positional form. Okay, the problem with the positional form is that sometimes we do not know this value Cs, constant value, we may not know all the time. So that we need to sometimes eliminate it so that we don't need to what we call the velocity form. What we do is take the Cn minus 1 at the previous time, and so everything convert back to the previous time, Cn minus 1. Okay, everything goes back to the previous time. So once we get the equation 2 and 3, we just minus them so that we can remove Cs. So what we get in this form, in terms of difference form, Cn minus 1, and the Kc part for En, the Kc1 was for the En minus 1, and this one for the En minus 2, and this is called the velocity form. Okay, another form in terms of the difference of the output signal, but the main thing is remove the Cs, because we do not know Cs problem. Sometimes we can have problem with what we call integral y naught. So this is normal form, and if we take the Z transformation of this one, okay, it's just Cz, and this one is a delay by n minus 1, so it's just Z minus 1 Cz, and everything else is just simple Z transformation issue. Is n minus 1 to Z minus 1 here, is En minus 1 Z minus 2 here, and so we will get the, in this form, we want to get the discrete transformation PI, the PID is just output over error input, so you get this form. This is the form. Okay, in terms of stability, as I said before, we look at the characteristic equation. For continuous system, the system is stable if the roots of its characteristic is lie to the left of the imaginary axis, we said before. And since the relationship, which is Z, E, T, S, is this form, as if we put S in terms of the real domain, the imaginary axis, then we're going to get Z in this form. So this is a complex number with magnitude E alpha t. But we, if S lies to the left of the imaginary axis, okay, which makes the system stable, then alpha here has to be negative. And if alpha is negative, then Z, magnitude of Z has to be less than 1, which is the rule of stability in discrete time system. Okay, so for continuous, in the Z domain is on the left of the imaginary axis. For discrete time, is inside the unit circle, is stable. Other than that, it's not stable. We see in terms of the in the diagram form, anything on the left is stable, and when converted to what we've done, it has to be within the unit circle, and it is stable. So the dynamic system of the system is stable if the poles or roots of the characteristic are located on means on the imaginary axis, just stable on continuous oscillation, or inside the unity circle in a complex axis which is less than 1. Basically, the characteristic equation, as we've seen before, the last lecture, is just one Hg paired dz and so on. Similar to the characteristic equation of the continuous domain, only that now we have introduced the Z domain, and we have what we call the whole element. Okay, that's just simple. Everything else is the same. Discrete time, continuous. In terms of designing of controllers, we can use the normal tuning methods. Okay, the only advantage is here the controller we can put in different form. So it doesn't have to be PPID. We can design our own DZ controller for certain aspects, which is another topic on itself, design the discrete time controller. But if we talk about PID, that's it. That's what we have seen. We can use it simply and similar to what we've done. You can try this question as a tutorial, and you'll be able to find the closed loop discrete time response, and the ultimate control lane will be more familiar what's happening using discrete time system formulation with additional of the whole element, the sampling and working into with the Z domain. Okay, thank you very much.